Okay, in this video we'll be going through the 2014 Level 3 Mechanics Exam. Question 1. Show that the period of rotation of a particle located on the equator of the Sun is 2.12 times 10 to the 6 seconds. So we know our angular velocity is equal to our theta all over our period, and therefore our period of rotation is equal to our theta all over our angular velocity. Now we can see here our angular velocity is 14.7 degrees per day. And so we can plug that in, 14.7 on the bottom. Now our theta is 2 pi. However, in this case, we're going to use 360 degrees. The reason for that is because our 14.7 is in degrees as well. And so we can put 360. And this gives us a period of 24.49 days. And so now that we have our period in days, we need to convert it into seconds. And so the way we do that is we get 24.49 times 24 times 60 times 60. Right, the reason why we do that is because we have 24 hours in a day, 60 minutes in an hour, and then 60 seconds within an hour. And this gives us a period of 2.12 times 10 to the 6 seconds. And as you can see, that is the answer we're trying to find. Now just a quick side tangent, this is not needed for this question, but I often get asked, how do I know that this period is in days rather than seconds? And we can figure this out through some dimensional analysis. Right, if we look up top, we have 360 degrees up top, right? And on the bottom, we have degrees per day, right? We get that from here. Now, if we redraw our equation with just our units, we have degrees all over degrees per day. And that is equal to our period, right? Now, we can redraw this as T is equal to degrees multiplied by day over degrees. Right, that's some basic level 1 maths, I assume. And so now that we have degrees on the top and on the bottom, we can cancel these out. And we get our period is in days. So that is how I know that our period is in days. And you can use this strategy to double check your units in case you don't know what to put. And if you want to learn more about this, I have a video on dimensional analysis on my channel. I think it's the first video I made. So check that out. Calculate the linear speed of a particle at the Sun's equator. Okay, so we know our equation for linear speed is velocity is equal to distance over time. Now, if you look at the distance that we're traveling, we have our Sun right here, and the particle is going along the equator. Now, if we look at this from a top-down view, we have our Sun. This is a top-down view. And we can imagine that the particle is going to move along the equator. Right? And so you can see that the particle is traveling in the motion of a circle. Now that means that the distance that the particle is traveling is the circumference of the Sun, and we know that the circumference of a circle is equal to 2 pi r, and therefore our distance covered is equal to 2 pi r. As for our time, we know that the time taken to complete one full rotation is just one period, and so our time is equal to our period. And so we can make that substitution where our linear velocity is equal to 2 pi r all over our period. Now we know our period, which is what we found in the previous question, is equal to 2.12 times 10 to the 6 seconds. As for our radius is given up here as 6.96 times 10 to the 8. So our radius is equal to 6.96 times 10 to the 8 meters. Right? And so we can plug in our numbers. Our linear velocity is equal to 2 pi times our radius, 6.96 times 10 to the 8, all over our period, 2.12 times 10 to the 6. And this gives us a velocity of 2,063 meters per second. There we go. Now it's important to note that in the answer schedule it says any answer between 2060 and 2070 is acceptable. This is just due to some rounding errors. Gravity may cause the rotating inner core of the Sun to collapse down to a much smaller radius. Explain how this will affect the angular speed of the inner core. So if the radius of the inner core shrinks, that means obviously our radius has decreased. And because our rotational inertia is equal to mr squared, if our radius decreases, our rotational inertia must also decrease. Now we know that our angular momentum is equal to our rotational inertia times our angular velocity. Now in this case, our angular momentum is conserved, and therefore if our rotational inertia decreases, therefore our angular velocity must increase. And so that's the theory, and you can write an answer in words based on that. The mass of Mercury is 3.3 times 10 to the 23 kgs. Mercury has a period of rotation of 5 times 10 to the 6 seconds. Show that a satellite needs to be positioned 2.43 times 10 to the 8 meters from the center of Mercury so that it remains stationary from the point of view of an observer on the planet. So what this question is trying to get at is geostationary orbit. What geostationary orbit means is that if we have our Mercury right here, and if we have a satellite right here, what that means is that the satellite is going to constantly look at the exact same place on Mercury at all times, geostationary. And so even though Mercury is rotating, and the satellite is going to orbit Mercury as well, the satellite is going to remain in the same relative position to Mercury. And so what that means is that the period of Mercury is equal to 5.067 times 10 to the 6, but because the satellite is staying in the same relative position to Mercury, the period of orbit of the satellite must be equal to the period of rotation of Mercury. Okay? So, now to solve this question, we know that our centripetal force must be provided by Fg, and we know that Fc is equal to mv squared over r, and we know that Fg is equal to g, big mass, little mass, all over r squared. Now again, we can cancel out our little masses on both sides. Remember, our little mass is the mass of the satellite, and our big mass is the mass of Mercury. So we can cancel those out, and we get that v squared over r is equal to g, big mass, all over r squared. Now as for our velocity, this is the velocity of the satellite, and our velocity is equal to 2 pi r over t. The reason for that is the same reason why our particle had a velocity of 2 pi r over t. The satellite is going around in a circle, therefore the distance is the circumference of a circle, 2 pi r, and it has a time of a single period. Now what that means is that v squared is equal to 4 pi squared r squared all over t squared, and so now we can make that substitution. We see that 4 pi squared r squared all over t squared divided by r is equal to gm all over r squared. Now simplifying this down, we get 4 pi squared r all over t squared is equal to gm over r squared. Almost forgot that. Now we can move this r squared up here, and we get 4 pi squared r cubed all over t squared is equal to gm. Now we want to rearrange for our radius, and we get r cubed is equal to gmt squared all over 4 pi squared. Now obviously to get r by itself, we can cube root the entire thing, and we get r is equal to the cube root of gmt squared all over 4 pi squared. Now plugging in our numbers, we get r is equal to the cube root of our gravitational constant, which is 6.67 times 10 to the negative 11, times the mass of Mercury, which is 3.3 times 10 to the 23 kgs, right? And our period is equal to 5.067 times 10 to the 6 squared, and that's all over 4 pi squared. And this gives us a radius of 2.43 times 10 to the 8 meters. And as you can see, this is the value that we're trying to find right here. A space probe spins around an axis as shown below. An instrument comes loose from the space probe. Explain why this loss of mass will have no effect on the angular speed of the space probe. So the reason why this has no effect on the space probe, if we draw our space probe as a little circle, right? Simplified version. If a little piece of the space probe comes loose, that little piece will contain angular momentum, right? That little piece has angular momentum in and of itself. And so we know that the angular momentum is equal to I omega. And based on what we said before, that little piece contained angular momentum. And so based on what we said before, if that mass is lost, that means the angular momentum of the space probe must decrease. Now, because a little piece of that space probe is also missing, the rotational inertia of the space probe will also decrease. Now, because the angular momentum of the space probe has decreased and also the rotational inertia has decreased, this means that the angular velocity can remain the same. And so you can write that in words. Okay, moving on to question 2. A pendulum is set up as shown in the diagram. The cord length is 1.15 meters and the mass of the bob is 1.8 kgs. Calculate the time it takes for the bob to swing from one end to the other. Okay, so we know the time taken for the pendulum to swing from one end to the other, back to where it first started, is 1 period, and so the time taken for it to swing from one end to the other is half the period. So we can just find our period and then divide it by 2 and we get our final answer. So we know from our equation that our period is equal to 2 pi square root L over g, where our L is the length of the pendulum and g is our acceleration due to gravity. So we can plug in our numbers as we have all our values, and we get t is equal to 2 pi square root 1.55 all over 9.81, and that gives us a period of 1.25 seconds. There we go. Explain how the forces acting on the bob change the bob's speed as it travels from the point of release to the center. Okay, so if we draw the bob at the point of release, which is at max displacement, right? That's the equilibrium position right here. We know that on the bob there is going to be a weight force acting down, and there's also going to be a tension force up the string. And so therefore, using our vectors, we have a tension force up here, a weight force coming down, and as you can see, there is a resultant vector. This is our restoring force. Now, at the point of release, the bob is going to be stationary for like a hair of a second, and then that restoring force is going to cause the bob to accelerate, making the velocity of the bob increase. The speed of the bob is going to increase, right? And so the speed of the bob is going to increase, and so the bob is going to move towards the center. Now we can imagine when the bob is now at the center position, like this, our weight force is going to be still acting downwards, and our tension is still going to be up the string. Now if we draw a vector for this situation, we can see that the tension goes directly upwards, right? That's our tension. And our weight force comes directly downwards. And as you can see, there is no restoring force vector, and so therefore in the middle, there is no restoring force. And therefore in the equilibrium position in the middle, the bob does not experience any acceleration, and therefore at the middle, as the bob experiences no acceleration at this point, the bob's speed is constant. And let me label this. This is Fg, this vector, and this is our tension force right there. And again, like always, obviously you can't just write this, what I've written these diagrams in the actual exam. You have to write an explanation based on what I've told you. Okay, so the bob is released again in such a way that it swings in a horizontal circle with a radius of 0.29 meters. By first calculating the size of the angle that the cord makes with the vertical, show that the tension force in the cord is 18 newtons. Okay, so if we just draw a simplified version of this setup, we have a bob right there. This is the equilibrium position. And we have our radius right here, which is 0.29 meters, right? This is 1.55 meters, and this is our angle theta, which we're trying to find. And obviously, this is now a right angle. Okay, so because that is a right angle and we have two sides that we know of, we can find the angle theta. So we have the hypotenuse and the opposite side, so we can use our sine relationship. So our theta is equal to the inverse sine of 0.290 all over 1.55, and therefore our theta is equal to 10.78 degrees. And this is also equal to 0.188 radians. Okay, so now if we draw another diagram of the bob, we can have our bob like that. It's essentially the same diagram, right? And we know our bob is going in a circular path like this. We know that the bob is going to have a weight force acting down, and this is going to be equal to mg. We also know that there's going to be a tension in the string, and we also know, because it's in circular motion, that there must be a centripetal force provided. And so now we can draw a vector diagram based off that. We have our mg going straight down. We also have our tension force coming up like this, right? And we have our Fc like so. And we know that this angle right here is our theta. So as stated in the question, we're trying to find our tension force. We know our weight force, we can find that out. We have the mass of the bob, and we obviously know the acceleration due to gravity is 9.81. And we also have our theta, because we found it up here. So now as we have our adjacent and we're trying to find our hypotenuse, we can use our cos relationship. We know that cos theta is equal to the adjacent side all over the hypotenuse. We're trying to find our hypotenuse, so we can rearrange. So our hypotenuse is equal to the adjacent side all over cos theta. Now we know our hypotenuse is the tension force and our adjacent side is the weight force. So we can plug that in, saying our T is equal to mg all over cos theta. And so therefore, as the mass of the bob is 1.8 kgs, our T is equal to 1.8 times 9.81 all over cos 10.78 degrees. And this gives us a tension force of 17.97 newtons, which is basically the same as 18 newtons. There we go. And as you can see, that is the force that we're trying to find. Calculate the speed that the mass must have been given when released in order to attain a horizontal circular path of radius 0.29 meters. Okay, so right off the bat, we should know that our equation for our centripetal force is mv squared over r. And so we can see here that the equation for our Fc has v squared in it. So we want to rearrange our Fc equation so we can get our velocity. Now the problem is that we do not know what our centripetal force is, and so we need to find that. The way we can find that is through our vector diagram. We drew this in the last question. We have our mg coming down, we have our tension force coming up here, and we have our Fc coming down here. Now we found out the value of our tension, and we know the value of our mg, and as this is a right angle, we can use our Pythagoras. So we know our tension is equal to 18 newtons, and we know our mg is equal to 1.8 times 9.81, right? And so therefore, we know our Fc is equal to the square root of 18 squared minus 1.8 times 9.81 squared, and that gives us an Fc of 3.63 newtons. Okay, so now we know our Fc, we can rearrange our centripetal force equation to find our velocity. So we know that v is equal to the square root of Fc times r all over mass, and therefore our velocity is equal to the square root of 3.63 times 0.290 all over 1.8, which is the mass. And that gives us a velocity of 0.736 meters per second. There we go. Okay, moving on to question 3 now. A system consists of two discs, A and B, attached together with a light cord. The surface that A and B slide on is frictionless, and A has a mass of 0.517 kgs, and B has a mass of 0.64 kgs. B is stationary, and A is moving towards B, with a speed of 1.21 meters per second. Show that the speed of the center of mass of the system is 0.521 meters per second. Show all your working. Okay, so we know that momentum is equal to mass times velocity, right? In this case, the velocity that we're interested in is the velocity of the center of mass, and the mass in this case is the mass of A plus the mass of B, right? Because we're taking into consideration the entire system. And so we can plug that in. The momentum of the entire system, which we can write as PS, is equal to MA plus MB times the velocity of the center of mass. Now we can rearrange this equation for the velocity of the center of mass, and so the velocity of the center of mass is equal to the momentum of the system all over the mass of A plus the mass of B. Now we have the mass of both A and B, but we don't have the momentum of the system, so we can find that out. Now in this system, A is the only disk that is moving, and so therefore it is the only disk that carries momentum, because again, momentum is equal to mv, so if velocity is 0 for disk B, that means its momentum is 0, right? And so the momentum of the entire system is equal to ma times va, where va is the velocity of disk A, plus mb times vb. Again, vb being the velocity of mass b. And so the momentum of the system is equal to mass A, which has a mass of 0.517 times its velocity, which is 1.21, plus mass B, which has a mass of 0.684 times its velocity, which is 0. And so therefore, as the velocity is 0, that just cancels out because anything times 0 is 0. And so the momentum of the system is equal to 0.62557 kg meters per second. There we go. So now we can plug that number back into here, right? And we get the velocity of the center of mass is equal to 0.62557 all over the mass of A, which is 0.517, plus the mass of B, which is 0.684. And that gives us the velocity of the center of mass as 0.521 meters per second. And as you can see, that is the velocity that we're trying to find. Both A and B collide, and after the collision, they are moving at right angles to each other. A receives an impulse of 0.25 Newton seconds. Show that the speed of B after the collision is 0.365 meters per second. So we know that impulse is just another way of saying change in momentum, so our change in momentum is equal to 0.250. Now it's important to note that, as always, momentum is conserved, so that means that the change in momentum that A experiences is equal to the change in momentum that B experiences. Now because B had a momentum of 0 initially, its change in momentum is going to be the same as its final momentum. Because if it's 0 initially and then it increases by 0.25, then its final momentum must be equal to 0.250, right? And so therefore we can say that for B, the change in momentum is equal to the momentum finally. And so, as we know, the momentum finally is equal to mass times velocity, as always. And now that we know that the final momentum is 0.25, and we know the mass of B, we can now rearrange for its velocity. And so its velocity is equal to the momentum finally all over its mass. And so therefore 0.25 all over 0.684. This gives us a velocity of 0.365 meters per second. And as you can see, that is the velocity that we're trying to find. Determine the size of the momentum of disk A after the collision. Okay, so we know from previous questions, I think it was part A, that the momentum of the system is equal to 0.62557, right? kg meters per second, right? As we know, momentum is a vector, so in order to find the momentum of disk A, we need to draw our vector diagram. So as seen in previous questions, we know that A kind of moves off in this direction here, and B kind of moves off slightly downwards. So we can draw A like so, and B comes down like this, and therefore we can see that the resultant is like so. Now this resultant is obviously the momentum of the system, right? If this is the momentum of our B, we know that's equal to 0.250, and we're trying to find the momentum of A. Now, as this is a right angled triangle, we can simply use our Pythagoras. So the momentum of A is equal to the square root of the momentum of the system, which is 0.62557 squared, minus the momentum of B, which is 0.250 squared, and that gives us a momentum of A as 0.573 kg meters per second. There we go. The discs continue to slide until the cord is fully extended. When this happened, both discs change their speed and direction. By considering the forces that act on the discs, explain why the momentum of the system must be conserved. So we can imagine a simplified version where we have our string in between our two masses. Now I've drawn the string like that to signify that the string is loose. Now when the cord is fully extended, we can imagine it as a straight line, right? It's fully taut. The only force that is going to be present is the tension force in the string, right? Now because this is an internal force, not an external force, the momentum of the system will not change. Neither will the velocity of the center of mass. The velocity of the center of mass will remain the same. Now remember that the surface that the discs glide on is also frictionless, and so there's no force acting on the discs from the surface. So there are absolutely no external forces in this scenario, and so therefore, as there are no external forces acting, momentum must be conserved. And so you can write a lovely answer based on that theory. Sweet as. And with that, we are done. Sweet as.